It's all about striking the right balance between learning about new upgrade and maximizing the performance of that specific race weekend.
So when we talk about developing the Formula One car, this can be two parts. First part is aerodynamic development, and that is the wetted surfaces of the car that you see from the exterior. And the second part is about the chassis development. Those are the underlying parts such as suspension, steering and brakes. It's fair to say the car is constantly evolving. In addition to the underlying development rate of the car, there are also event-specific developments that we target, such as a low downforce rear wing for events such as Spa. It's fair to say that the development direction can also change and try to ensure that we always achieve maximum performance. We work closely with the aero group to optimise the solution ahead of the final release. We then work closely with manufacturing to ensuring that we achieve the best quality components. The biggest challenge is always time. The quicker you can go from the tunnel to the track and positively impact the race weekend, the better.
The process that we would follow in terms of putting together an aerodynamic upgrade is, first of all, identify what we want to improve in terms of the airflow around the car. The second part of it is then to come up with different ways of trying to target that with the geometry and within the regulations that we have. And then we would do a mixture of testing, so we'd run simulations to try and understand if we can manipulate the flow field in the way that we want to. And then if something was to be successful from that test, we would then take it into a wind tunnel test and try and understand if it's improved the aerodynamic performance or not. Once we get an update to the track, within the aero department, we're probably already well into working on the next upgrade package to continue driving the performance of the car. There's a bit of a feedback process because we can look at how what we've already released has behaved and then decide if that will steer what we might do next as a result. The areas we change might be specific to the event. So for example, low downforce circuit, we'd be looking more to bring, say, a rear wing package, or for other events, it would be more of a general aerodynamic upgrade.
The data we get is really very specific to the simulation we're performing and also the question we're trying to answer. If we're trying to determine whether a new lightweight part will be strong enough, then its stresses and its forces are the most important thing. If we're trying to determine whether an upgrade will make the car faster, then that lap time improvement and how that lap time comes is also super important. So we get a vast array of data, but it's very specific to the particular question we're trying to answer. And once we have it, the job of then myself and other people in similar roles to me is to look at all those squiggly lines and find that lap time. We start at a component level. Are things going to be strong enough? Are they going to be light? All the way through to lap simulations. Is it going to make the car go faster? How do we make the car go faster? And then we also have the driver in the loop simulator, the hybrid between the real world and the simulation world. And it's a place where our real drivers, our race drivers, can jump in and they can experience a virtual version of the car before it ever becomes reality. Now, in a cost-cut world more so than ever, it is vitally important that we use these simulation tools to determine whether our upgrades will deliver on track.
Items we put on the car and performance we add to the car isn't all surface level. There are items that are underneath the surface that people just won't see, that we spend a lot of time developing. This can involve suspension work, which we've got in manufacture at the moment. Also steering tests that we do, so various different mechanical items on the car get updated and tested throughout the year. And we put quite a lot of emphasis on the manufacture of those items internally. There's a lot of complexity in those components, and they're very tightly toleranced to make sure that it performs as expected. So the process for manufacturing aerodynamic composite type components is a big team effort. There are a lot of different departments involved. Aero will release a surface through to design. Design will then produce a model or a drawing of what it is they require. When it comes through into manufacturing, we'll then produce a pattern, then a mould, then come into the composite world and they'll laminate the component as such. Then we'll look to do pre-fit work so that it's quality control, quality assured. There'll be a T&D stage, so test and development steps involved, certainly for some of the more Class A or the bigger components. There's also non-destructive testing. They'll be involved at various stages and they'll scan the components for structural integrity. So as you can see, it really is a big team effort. So to manage the workflow across the factory, we put a great emphasis on planning. For a new car, for example, we'd probably start planning that a year in advance of the actual filming day or shakedown. Performance updates, we'd probably start planning that a couple of months ahead of when we need to be delivering. In addition to this, we also have the ability to be very reactive so that we can respond overnight or in an afternoon if we incur damage at a weekend or if we need to bring forwards a performance item.
So once an update makes it to the track, the way that we analyse it will vary depending on if it's an update package or if it's just a single component. For those smaller components, they're a bit easier to fit at the circuit. We have hundreds of sensors all over the car that allow us to measure the aero data. This is streamed real time. We're able to do initial analysis on the updates when the car is still out on track. For the larger aero upgrades, it's a bit more difficult to fit that into a single race weekend, and so we have to make sure at the previous races we're collecting enough data so that we've got something to compare back to. When it comes to analysing the aero update and checking that it's had the desired effect on the performance, there are kind of three main areas that we look at. So firstly, we compare back to the previous component and check that we are actually getting the performance improvement from the aero sensors on the car. Secondly, we're looking for any characteristic changes. So certain components may improve the performance in particular corners or particular phases of the corners around the circuit. And then finally, we compare these results back to the expected results from the wind tunnel as well. This wind tunnel data also feeds into our simulation tools, and that allows us to see which corners around the circuit we think that the performance improvement will be the largest.
It's all about striking the right balance between learning about new upgrade and maximizing the performance of that specific race weekend. On Friday, we try to learn as much as possible on the new upgrade. On Saturday and Sunday, we try to maximize the setup towards qualifying a race. We need to know exactly what the expectations are in terms of car balance. We need to see if we can match those expectations, if they are translated into the behavior on track. The driver feedback is pivotal when we are bringing a new upgrade and knowing if it performs as intended. The drivers are really good at picking up specific events around the lap and pinpoint them to the engineers. So we can gather after the debrief and look at those specific examples and find out exactly what was going on at that time and if the upgrade is doing what we were intending to do.